The most important result in last section is about the Pcr test. Okay. We use an integral test to prove that. So here's the result, the P series test. We can this is for the series and 1 of n to the power p. Okay, and this has a following result. I remember this is a convergent, right? If p is greater than 1. Divergent if p is less than or equal to 1. Okay, p is some fixed number. Okay, we prove that using the corresponding integral. Okay, and it is proved using the following fact. Okay. The integral from any number, okay, and this is x to the power dx, okay, and this one, when p is greater than 1, actually this is going to be p minus 1 if p is greater than 1. Otherwise, it's divergent, okay, and here's a is a positive number, then this can be actually infinity if p is less than or equal to 1. Okay, so this is the corresponding integral. Okay, so using that, then if you're given this series, for example, right, and whether this is convergent or divergent, that's obvious now, right? Because this is just a p series, right? Yeah, this is a p series number scale. This is a p series where p is going to be square root 2. Square root 2 is greater than 1, so it is convergent. Okay, you can actually estimate the series. Okay, you can even estimate the sum. Okay, you can estimate the sum. Okay. All right. So today we are going to now look at this series, right? All the terms are positive. So there's only two possibilities. Either it's infinite or it's a finite. Okay. So look at this series, right? Look at this series. You only have two possibilities. Either finite. So that means convergent. Okay. Or yeah. It's an infinity. So in this case, divergent. Now, yeah. So you cannot just state for this series. Okay, you cannot just state it's convergent. You have to say, you have to quote some results already proved. Okay, you have to say it is convergent by the P series test. You have to say that. Remember, you are not the jury. Okay, you don't need to give a reason to prove someone is guilty. Just say, I feel like he's guilty. He's criminal. You are the lawyer. Okay, you have to give evidence to prove, to show why this guy is, right, is guilty or not guilty. Okay, so you cannot just claim. Okay, clear? Yeah. So if you just put a statement that without any explanation, you will not get full credits. Okay. Right. So this is a piece. It's already proved. We use the integral. You don't need to repeat repeatedly using integral test to prove. Okay. This whatever it's already proved in the book, you can quote it. Okay. You can use it. Okay, so when you do the when you work on the test or you know do quizzes, you just look at the page. You can even mention the page number by the Pcr test or integral test. You can put in section 11.3, for example. Then I conclude that. Okay, so you have to say a few words about that. So this is the reason there's only two options here. Sometimes the series is the limit doesn't exist, but in this case, because every term is positive, so every time you add one more term, you get a larger number. So that's why it's going up this sequence of numbers, which are partial sum of the series. Okay, and so there's only two possibilities: either finite or the limit is finite or infinity. So when it's infinity, we say it's divergent. Okay, so now let's consider another series. Okay, consider this series and start from capital N, where each of n is always positive or non-zero. Yeah. Then you look at the partial sum, right? This partial sum is another sequence. Okay, this sequence clearly is going to be this is from n, right? Sn plus 1. So it's increasing. So for a sequence, an increasing sequence, there's only two possibilities: either it approaches infinity, or it has a finite limit. So if the first case, if this series has an upper bound, this is an upper bound. So there is upper bound, then the limit exists. Okay, this is going to be finite. Not only just exists and less than or equal to n. Okay, exists and finite. Okay, so in this case, the series is convergent. So case 2, if this sequence has no upper bound. Okay, this sequence has no upper bound. Then in other words, then the limit of sk is going to be infinity. It's going up, right? So in this case, the corresponding series is divergent. So this implies this series is convergent. Okay, and here this series is divergent. Okay, so the question is, how do we check whether this is a finite or infinity? Okay, to check that, we have so-called comparison theorem. Okay, sometimes the series itself is complicated, but we can simplify. Okay, so this is the comparison test. The comparison test says that if you have a two series, okay, and then if this is true for n greater than or equal to some capital N, okay, then this series, okay, is less than or equal to that series. That sounds obvious, right? Okay, I think this is obvious. Okay, right? Don't need to express. Just add the partial sum, and then set from this inequality. Then of course, if you take a limit, this inequality holds. Okay, so this side is always positive, right? It's the same. Okay, then you can tell which, if the one on the left hand side is infinity, then the one on the right hand side is infinity, right? If the one on the right hand side is infinity, finite, then the one on the left hand side is finite. Okay, so how do you conclude that, right? So it's obvious, right, to which side You know, in order to, yeah, so you can conclude that, okay, if this is an infinity, then the one on the right-hand side is also infinity, right? Right? Some number is greater than or equal to infinity, then of course it's infinity. If the series on the right-hand side is finite, then that forces the one on the right-hand side also finite, because it's less than or equal to a finite number. Okay, and this is a pretty useful result. Okay, we can take a look at this one. Okay, remember we proved that it is convergent using integral test. Okay, so we did that before, right? So we can say that we can prove this is convergent. Oh, sorry. Using the integral test, and because I can evaluate the integral easily using arctangent. Okay, using the integral test. Okay. Okay, so using the integral test, I'm not going to do that. This is in the last section. Okay, so what I'm trying to do right now is using compression test. My n is going to be n squared plus 1, which is positive, right? And this, I can make it smaller, larger. It's 1 over n squared, which is a bn. Okay, so as I can see that by the above compression test, right? At least you have this one. But this, the one on the right-hand side is finite, and why it's finite? You can say by the p-series test. Okay, you have to remind people you're using the p-series test. You cannot just say it's a finite. It's obvious. Okay, you have to quote the result. You have to put a note here. Okay, so when you do the do the homework, yeah, just write. Yeah, you just put a remark here. Okay, that's enough. Yeah. Then this is finite as one on the right-hand side. Of course, it's between 0 and the finite number. Of course, it's finite. So that implies this implies it's finite. Okay, that's enough. So this is convergent. Okay. I think a comparison test is sometimes easier to use to prove it's convergent. Okay, for example, if I modify this series in this form, now can you use a integral test to prove it? I think it's very difficult because you cannot evaluate the corresponding integral. Yeah. So if you use the integral, how do you know this is convergent, right? You still have to use a comparison test. Okay. If we use the integral test, okay, then we have to show that this integral, right, is finite, right? It's convergent. Okay. Then you still have to use a comparison test to prove it's convergent, because otherwise you cannot find the antiderivative of this function. It's no way. Okay, right? So it's the same. So why have to go through the integral test? We just use a comparison test directly, right? Now for integral, we do have a comparison test too. It's called the comparison theorem, right? So we don't need to do that. So what I'm trying to do is here, I can simplify. This is greater than 0, okay? So just remove the one term in the denominator. if you remove one term in the denominator, you get a P series, and that's my Bn. Okay, right? Right. Then you have this, which is a finite. Okay, and you still have to say that by the P series test. Okay, then so it's a finite. Is the one on the right hand side, left hand side is also finite. Okay, so that's why it's convergent. Okay. So you can say for one more word. That's why, you know. Okay. Then you can say convergent. Okay, because it's a finite. It's convergent. Okay. Because this series is a limit is always the limit is a limit always exists. Is a finite or infinity, right? That's only two possibilities here. Not like other limits, you're not sure. That sometimes doesn't exist. Okay. Now the trouble here is, here's another one. Okay. Okay, so this one. Think about how to do it. Okay. Yeah. So this is a good example to show you whether we should use an integral test or comparison test. Okay. So n start from 2. N start from 2. Okay. Yeah. Try to find some methods. At least I have 2 solutions to this problem. Okay, I'll let you to think about first. Now you have to get some idea, feeling, right? Why it's convergent, why it's divergent. Then you try to prove it. Okay. So this is AN. Right, this is AN. And clearly AN is a greater than 0, right? So are we able to compare with some BN? Well, simplified. I think it's possible, but you have to, you cannot just say it's less than or equal to 1 and then that's a mistake. The reason is that the denominator is smaller than n squared. So you have to go the opposite way. So that requires you have a very good mathematics to get a good estimate. Okay. So I can put a constant here. I can put a constant here, but I can determine it later, maybe 2 or maybe 3 or maybe 4. Okay, I think 2 is enough. Okay, that's my BN. Okay, but this is the most difficult solution. Let's try I can try and see 2. Probably 2 is enough. Okay, and let me try this. Okay, let's try, yeah, put a question mark here. Where's the window? So you get 2 squared less than or equal to n squared minus n. then that will be 2n squared minus 2n. So what I'm going to do is move 2n to the left side and move n squared to the right hand side to n squared. So I divide by n, so 2 is less than n. And those are the three equivalent to inequality. Then it's clearly, because our n is greater than or equal to. So clearly this is always true. Now, you may ask me, how do you know this is equal to that? Well, I cannot say this is not true, right? So I just enlarge the numerator, okay? So if you can figure out that, then you're done, okay? So let me repeat again. So this is my an, which is 1 over n squared minus n less than or equal to 2 over n squared, which is bn. Okay, then we have, right, it's less than or equal to, okay, and this is a convergent because twice of the piece is P series, so it just buys the Pcr test. Okay, so that, right, so then you conclude that okay. Now, I think very few students will find a good upper bound. Okay, it's pretty challenging. Right. If you can quickly figure out this already, that means you really have a very good training in mathematics. Okay, you have no problem to study. Choose math major. Just kidding. But anyway, so but gradually that you probably been after doing enough exercise right now. After doing enough exercise, you probably can also quickly figure out this. Okay, so this is a good solution. So the next one I'm trying to do is you look at this series, right? And this is so special, so you can fact this denominator. Okay, so actually you can find the partial sum. Use the original definition. Okay, and the reason is this term can be decomposed into two. Okay, this can be 1 over n minus 1 minus 1 over n. Okay, so that means the partial sum will be 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3, and keep it going, and k minus 1 minus 1 over k. So actually, this partial sum is just equal 1 minus 1 over k. Okay, so that has a limit. The limit is just 1. Okay, so we not only show this is convergent, we only get the exact value, which is going to be 1. Okay. Yeah, this is also proof, right? It's convergent and equal to 1. The third one, I just consider n, I can use the integral test, okay, which is equal to f of n, where f of x equals x squared minus x. And clearly this is f of x is positive, decreasing on the interval from 2 to infinity. Okay, right? So whether this series is convergent depends on integral. It depends on this integral from 2 to b, right? F of x dx. I want to see what is this limit. And you use the same idea, actually decompose it. You see, it's just like what we did. This is going to be 1 over x minus 1 over x, right? 1 of x minus 1 of x. So the antiderivative will be x minus 1 and x minus x, right? Evaluate the two endpoints. Okay, so you can combine them first. So I get natural log of b minus 1 over b minus natural log of 1 over 2. So that is so the limit is going to be natural log of 1 is 0 minus natural log of 1 over 2, which is natural log of 2. That's a positive number. Okay. So this integral is going to be natural log 2. It's convergent, right? Then you can say that by the integral test, I remember the integral is in the middle, right? It's less than or equal to n equals 2, and here's n squared, and no, so n minus 1, right? And this side n minus the first term, I think it's 1/2. So you can get an estimate of this. Okay. So in other words, it's less than the 1/2 plus natural log of 2 greater than or equal to natural log of 2. Actually, it's going to be 1, right? But here we cannot tell, this just, we only get this estimate using the integral test. Okay. This integral test as a method is good. Sometimes if I modify the problem a little bit, you may have to use the integral test. Okay. For example, if I ask you to check, it starts from 3, like this. Start from for 2n here. Then and you cannot easily find the partial sum. Okay, you have to use you probably can use a comparison test, but you cannot use you cannot find the limit using partial sum. Okay, yeah, but you can use a comparison test. The question is, what kind of constants we can put here for n greater than or equal to 3. Okay. Yeah, think about it. Can you figure out this constant? If you're not sure, put 100. It's guaranteed. Okay. If you put a 3 on the top, then this n must be log greater than or equal to some another number. Okay. So try this 3, right? If you try 3, and then you'll get n squared. Now this is equivalent to n squared is less than or equal to 3, n squared minus 2n, right? Let's try, right? So n squared less than or equal to 3, n squared minus 6n. So that's going to be 6n less than or equal to 2n squared. It's equivalent to 3 less than n. Great. It's perfect. So then you can use a comparison, and then you can use a comparison test to prove this convergence. Okay. But you have to prove this, whatever you claim. You cannot just assume, right? This is a proof. Yeah, put there. Okay, then you can use a comparison test. Then you can use a comparison test. Okay, then this is a finite. Okay, right? That's this is by the P series test. Okay. We already proved that using integral test, this series is convergent. So you just use it. Okay. All right. So here's another problem. This starts from 2 square n minus 1. All right, is this series is a convergent? Let me use yeah. So I'm going to change it -1 to +1 later. Okay. So first of all, let's see why it's convergent, why it's divergent. Okay. Which one we're going to compare with? I think it's going to be divergent. This is my series, right? So I have to put on this side. Clear? Right? then you integrate, add them together. Right? I know this side is going to be infinity. This is by the Pcr test. Okay, P is going to be 1/2, it's less than 1. So that forces the sum on the right-hand side is infinite. And this implies okay, so it's divergent, right? Okay. Now, if I change it to this, okay, can you show that it's divergent? Okay. I think it's still divergent. The question is how do you prove it? Think about it, okay? I give you a half minute. Yeah, you can grab, you can try to put some ideas in. All right, I hope you got it. Some ideas, right? I want to prove it's divergent. So that means I have to find, if I use a comparison test, I have to prove some constant here, right? Then the one on the left-hand side is infinity, then pushes the one on the right-hand to be infinity, right? So the question is, how can I figure out this constant? This constant cannot be greater than 1, should be less than 1. So we can put a constant in the, we have to guess and try, okay? That's the only way, you know. Yeah, we can put a constant here, right? Some constant, maybe 2, maybe 3. I'm going to try 2, okay, to see if we're able to do that. Okay, so 2 square n less than or equal to square n plus 1. I put a question mark here. I'm going to simplify it. Oops. Right, I didn't know at the very beginning what constant, small constant I should put there. So it's going to be square n plus 1 less than or equal to square n, right? Cross product. Then I think that's good enough. So n greater than 1 guarantee all the above inequality holds. Okay. Then I have the following identity. Right. So therefore, right? But the one on the right hand side is the infinity. This is by the Pcr test. Okay, P is going to be 1/2. It's just every time multiplied by 2, that 1/2 is okay, right? So that implies, this implies the one on the right hand side, the sum is going to be infinity, okay? Is there any other method we can solve this problem? At this moment, I don't have any better method. Okay, you have to use, if you have to use a comparison test, you have to find another lower bound, simple lower bound. Okay, the integral test does not work, right? Because if you think about this, anyone in this class can evaluate this integral? No. I just quickly said no. Maybe you can use a substitution, right? Possibly. Let's try, you know. I let u to be square x. Possible, right? So du equals, right? And that is going to be 2u dx, right? So dx is 2u du, right? Not too bad, right? Yeah, I said 2 earlier. Yeah, this is going to be square root 2 to infinity. And here u plus 1 dx is 2u du. Whoa, actually we can evaluate this integral. We're just lucky. Yeah, okay. Okay, then the antiderivative of the above function is also simple to get. Okay, the antiderivative. How can I find the antiderivative? How can I? It's a long division, right? 2u plus 1, it's 2, and 2u plus 2, and the subtraction is -2. So that is, that's 2 minus, I think that's it, right? The remainder is -2. So the antiderivative is going to be 2u minus 2 natural log of u plus 1, and then evaluate to end point, and clearly this can be infinity. Okay, great. So we can use the integral test to prove that, because this time we can evaluate this integral. Not too bad, right? Yeah. Yeah. by the integral test. Yeah, this series from 2 this is infinity by the integral test. Okay, good. So there are multiple solutions for each problem. All right, so that's why now if you solve the problem using one method, maybe you try a different way. Ask yourself, is there any other method you can try to prove? Right? You can use it to prove it's divergent. But look at, you cannot prove it's divergent using, here's a wrong argument, okay? Wrong proof, okay? Here says that the limit, now we cannot use that. The limit of the nth term is going to be, the limit of nth term is going to be 0, but this does not guarantee the sequence as a series convergent. Actually is divergent, right? So no, I just said put a note to that. The limit of the nth term is 0. Okay, so the nth term approaches 0. It's inconclusive. You cannot use this factor to do anything. Right? You cannot use this to do anything. All right, so here's another problem. Please do. Sorry. Okay, so take a look at this series. Are you able to use at least, all the problems I'm discussing in this class here, you can use a comparison test. Okay, so try a comparison test first. Maybe a little bit challenging, find the correct series to compare with. All right. So I hope you get ideas. I'll give you a minute, right, to try. I think it's convergent. So how do I know that, right? Because n, remember this is a picture, right? This n to the n's power. This number goes too fast, right? But what I need is just, all I need is something like this one, right? 1 over n squared. This is a finite by Pcr test. I probably just compare with this. That's easy to compare. So that is going to be n squared if n is greater than 2, right? Clear. So, so you have this, right? So that's holds for n greater than 2. But you also check with what happens for n equals 1. I think that when n equals 1 is the same. So I'm going to change it to 1. N equals 1 is 1 to the 1 equals 1 to the 1 squared. So this actually holds for n equal to 1. All right. So this is going to be, right? And that's finite, right? This is by the Pcr test. All right, so I'm done. So that implies it's convergent. All right, we're almost done, right? We do one more exercise and we're done. And direct comparison is very, very, very difficult to do that, right? Remember that we trying to prove this, right? But I knew this is the series convergent because it's almost, if we ignore the term +1, right? This is the reason I know this is a convergent divergent because this series is almost equal to like that for sufficient large n, and that by the P-series test, this series is divergent. So actually we can use we just need to look at the term when n sufficient large, okay? So here's a so-called limit comparison test. It's much easier to use than the comparison test. Okay, so we are given a series, two series, A and B and B. So we take a limit. Okay, we assume that this is a L. Okay, the first case is that if L is between is a positive. Okay, so what happens? Positive and finite. Then these two series have the same convergence. Okay, you know why? Because AN over BN, okay, this is going to be, because it approaches L, so it's going to be less than 2L greater than or equal to half of L. Do you agree, right? So for N sufficient large, for N greater than some capital N, right? Because this approaches L. L is between half L and the 2L, right? All right, using this fact, I have a 2L constant times Bn. I also have half of L times Bn, okay, for N greater than capital N. Then I put a sigma. Now I use a capital N, right? I don't need to consider the first two terms, first few terms, okay? All right, now it's clear. Why it's clear? then my conclusion is conclusion. Conclusion is the series is finite if only if the other one is finite. If and only if the other one is finite. The equivalent. Why? Because you see, if a series of n is finite, so for this is finite, then you can show that the one on the left is finite. If the series of Bn is finite, then you can use the inequality on the right hand side to show that the series of n is finite. So they have the same convergence. Okay, and just from some large n. So you don't need, you can ignore the first few terms. Okay, and if you use this property, then it's easy to study the convergence of this series. Okay, this is my n. Okay, I just drop the constant term. I don't like constant, so I get this. I call the Bn. Okay, then you check the limit, and you will see that limit is going to be 1, because this is how do we how do we get the Bn, right? So the limit is 1. And 1 is a positive finite number, but we know that this is a divergent, okay, by the Pcr test. Okay, so this implies this is also fine. Okay. So more precisely, what we prove that because the limit is 1. So we actually what we get here is n is 1 over n plus 1, right? This should be equal to less than equal 2 times this, and greater than or equal to 1/2. Okay, and for some larger n, I think it's already true for even for n greater than equal to 1. Okay. Okay. Even let me check the right hand side. It's a square n less than 2 square n plus 2. Well, this is automatically satisfied. Okay. The non-trivial part is on this side. Okay. We already showed that this is true, right? And let me erase this. Yeah. Okay. Okay. So this is this is L, right? So this inequality holds. Okay, that's why. And limited comparison test actually is a comparison test. Essentially, it's comparison. You still have to compare those two series. Okay, you still have to compare those two series. Okay. And similarly, if you can do this problem, right? So your n is going to be n squared minus n. I just drop a negative n. So this is n squared, which is my Bn. Then you consider the limit, and the limit is going to be n squared here, n squared minus n, and the limit is 1. So that guarantees your n is less than or equal to 2 times L, right? This is n squared greater than half of n squared. So which one we need? Okay, so that's for sufficient large n. n greater than some capital N. I think all we need is this part is enough, right? And that is true for n greater than equal 2. Okay, so actually this n could be 2. Okay, okay, I don't need the other side. So that's why that is, that's why you have an n started from some capital N, right? And then you can determine that what is capital N. Okay, this is a finite by the P-series test. Okay, so that's why use a comparison, use limited comparison test. Yeah, it's a quick one. Okay, so you don't need to worry about what constant you can put. It's not easy to figure out that constant. But the user limited comparison test, you just need to put a 2 on the top of n squared. Okay, but for some sufficient large n, guarantee it. But then you check what is capital N you're going to put there. Okay, capital N is 2. Okay, that's all about today's class. I'm going to give the quiz right now.